Average value of a function. Think back to like Algebra 1. How is it that you actually find an average? Yep, add up a bunch of numbers. You divide by the number of numbers. That's it. So I'll just put it up here in shorthand. You add, then you divide. Add up all those numbers, then you divide by the number of numbers. Okay, so to kind of help shape where we're going to go with this, I want to ask you a question that I really hope that if you were sitting there working on your homework and somebody peeked over your shoulder and they saw the tall, skinny S with the, from like 0 to 5 or whatever, and they saw that and they're like, hey, what is that? And you said, oh, that's a definite integral. And they're like, well, what is that? My hope is you wouldn't be like, I have no idea, or you don't want to know, like, yeah, that kind of thing. I hope what you would say is it's an infinite summation of infinitely skinny little things, right? So what is a definite integral? It is an infinite summation. And that's going to help kind of guide us as we think about the average value of a function. So I'm going to kind of fiddle around with this space right here. So maybe just for a moment, please don't write these first two things down. Maybe just kind of watch and think with me. So to find the average value of a function, let me just propose a couple of functions here to you. What if we had a function that looked like this? And I put an interval on it. Let's say the interval was from 3 to 12. And it's a horizontal line. And I said, what's the average value of that function on the interval from 3 to 12? What would you say? 7. Because every single y value is 7, so the average has to be 7. Does that make sense? Okay. So what if I did something a little bit different? What if instead of a line like that, what if the line did this? And let's say it went from, say, 4 to 12. And let's say we went from like 0 to 5 right there. So again, that's linear. What if I said, what's the average value of that function on the interval from 0 to 5? What would you say? 8, right? So it's linear. So wouldn't the average be the midpoint? And so from 4 to 12, the midpoint would be a height of 8, and so the average value would be 8 because you'd have exactly half the line below 8 and half the line would be above 8. Does that make sense? So by looking at these graphically, we can kind of get away from the adding up all the numbers and dividing by the number of numbers thing. But there's one other scenario. I'm sure you've thought of it. What if instead of a nice linear function, the function we were dealing with looked like this? Oh, no. It was curvy. Up and down and around we go. It's curvy, and so that strategy of, just looking at a horizontal line or a slanted line, figure out the average, it's not going to work so well. So let's say we thought of some strategies. Let's say we were trying to find the average value from 0, and maybe this would be something you want to write down. Find the average value from, say, 0 to 10. Here would maybe be a strategy that you could take. You could say, I am going to look at this graph, and I'm going to find the y value here, here, here. I'm just going to keep finding y values all across this curve. Look at all those y values represented by the little blue dots. Lots of y values. I'm going to calculate all those y values, and once I've calculated all those y values, I'm going to add them up, and I'm going to divide by the number of y values. Would that be a reasonable strategy? It'd be reasonable, but what would it actually find? It'd be an approximation, right? If I did all that, that would be an approximation for the average value. So while it's a good strategy, it's not going to give me the exact answer. Okay, so how could I make my approximation better?
More dots.
More dots, right? So double or triple the number of dots, whatever. But even if I did like 10 billion dots in there, wouldn't it still be an approximation? It wouldn't be enough. Would not be enough. I agree. So if I want this to be a perfect representation of the average value of the function, the number of dots would have to approach infinity, and I'd have to add up an infinite number of really, really, really close little points, right? They'd be really close to each other. The number of them would be approaching infinity. What am I talking about?
Rectangle.
I'm talking about an infinite summation, also known as a definite integral. Okay? So if I really wanted to add up all those blue points, if the number of them was approaching infinity, what I'd have to do is this. Integral from 0 to 10. And let's just let's call this f of x. I don't know what it is as far as which function it is. I have to do the integral from 0 to 10 of f of x dx. What this is going to do, this is going to add up all the y values. Right? So if I knew what f of x was and I calculated the integral from 0 to 10, this would add up all the y values and I'd have this big sum, right? This big total. So then I need to divide, right? The way that I divide here is I'm going to divide by the width of the interval. And in this case, the interval stretches from 0 to 10, and so the width of the interval is 10. So I'll divide by doing this. That makes sense? Just multiply by 1/10. Same thing as dividing by 10. And this right here would be the average value of that particular function on the interval from 0 to 10. What I'm highlighting right now, this is the adding up all the numbers part. And what I'm highlighting in red, this is the dividing by the number of numbers functionally, is what we're talking about there. That would give us the average value of the function. So I want to give you a general rule for this, and then we'll do some practicing. The general rule is this. I'll say for the average value of f of x on I try to make this antiderivative really easy for you. So this is 1/3, of course. The antiderivative is x cubed minus x squared, using the power rule for antiderivatives. Make sense? Okay. Evaluator from 1 to 4. What I would do with this is I would plug in the 4. So that would give me 4 cubed minus 4 squared. And then I'd plug in the 1. That would give me 1 cubed minus 1 squared. And in doing that, let's see here, 4 cubed is 64 minus 16 is 48. So I'd get 1/3 of 48. And this just ends up being minus 0, doesn't it? 1 minus 1. So 1/3 of 48 is 16. That is your average value. Questions? One minus one is what? Man, I think that probably is deserving of a 0 on the whole test. No, I'm just kidding. So that would definitely just be a -1. Obviously, yeah, if you got to that point, you've obviously done pretty much all the calculus right. You just made a simplistic arithmetic error. As frustrating as that might be, that's all it is, so it's not the end of the world. Yeah. Okay, let's take a look at number 10. Similarly, I want to kind of help you set this up. If you've read this, you already know that Billy has a problem, right? Serious problem. Well, hey, during the first hour, he has no problem. But by the end of the 4th hour, he has a problem, right? He's eaten quite a few donuts. Yeah. Anyways, Billy, along with his problems, he is eating donuts at a rate of r of t equals 2t cubed donuts per hour. Hey, guys, I want to make sure this makes sense to you guys. The fact that I've associated the word rate with that unit, does that make sense? A rate of blah, 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 donuts per hour. Those go together. Okay. On the interval 0 to 4, it says, what is his average, keyword there, rate of donut consumption in donuts per hour? So it's important for us to realize you were given a rate, and it wants to know the average rate. So this is essentially asking us to find the average value of the rate. There's some deeper questions we'll probably get into a little bit later on in this section. But for now, I mean, if you have them, feel free to ask. But for now, we'll leave it at that. So I would say the formula for this would be 1 over 4 minus 0 times the integral from 0 to 4 of 2t cubed dt. This will give us his average rate of donut consumption, or the average value of r of t. So again, I set this one up for you. If you guys would, please take a minute, see if you can evaluate this. You did pretty well with that first one. Think of that as a review. Think of this as another opportunity to review what we did prior to Thanksgiving break. So give it a few minutes. Give it a shot. Let me just show you the mechanics of this really quick. Make sure we're all good. Hey guys, let's make sure your notation is rock solid. We don't want to have any people kind of going off the rails as far as notation, making up stuff. Obviously, 4 minus 0 is 4. Your antiderivative would be 1/2 t to the 4th. that's evaluated from 0 to 4. We would plug in the 4, and when we plug in the 4, let's see here, 4 to the 4th is 256, so it'd be 1/2 of 256, and then thankfully minus 1/2 of 0, kind of makes it easy. And then half of 256 is 128, and 1/4 of 128 is 32 donuts per hour. Okay, any questions? That's his average rate of donut consumption. That's a lot of donuts, yeah. Okay, cool. So let's go ahead and jump ahead to one more example using mean value. And I want to kind of introduce this to you like this. This is not a perfect example, but it's close. Well, think this through. Yeah, let's do it like this. This will be a better example. I was going to do something else, but let's do this. Let's say that you were driving your car, and we decided to graph your speed over time. And let's say that we could get a really good graph or graph of a function for your speed. So let's say we get your speed here on the x-axis, and let's say your speed does something like this. I don't know what that means, whether you're on the highway or the Highlands Ranch Parkway or whatever, but that's your speed. And let's say then we were able to find a function for that. And let's say then we did what we've been doing and we found your average speed, right? So tell me, would this make sense? If I graphed your average speed, if it looked like this, would that make sense to be your average speed? Why not? It's 2. Okay. How about this? Would this make sense for an average speed? Where should it be? Somewhere in the middle, right? That's what average means, right? It's a measure of middleness or an average of central tendency. And so, maybe something like that. That seems somewhat reasonable. Okay. So if my speed, which it should be because I don't have a teleporting car, if my speed is continuous, wouldn't it make sense that my speed would actually hit that average speed somewhere in there? Makes sense? And you can see in this case, it looks like it is about 3 times, right? Question?
Is that the same thing we did with the cops?
It's a little bit different. So there with the cops, we're finding the average slope. And this is already a graph of speed. And so what we did with the cops is we did not have really good data for speed other than from the speed guns, and those told us nothing. But what we did have from the cops is we knew a location and a location, and we knew a time, and so we were able to find the average slope of position.
Oh, okay.
Right? So it's like they're definitely related. It just kind of depends on what information you have.
Yeah.
Here I've got an exact graph of speed. So if the cops had this for our speed trap project, they could have been like, there, that's where you sped.
Yeah.
Right? They could just look at it and be like, there's your highest speed, you get an 80-mile-an-hour ticket or whatever. But we didn't have that information.
Okay.
So that would be, what that would be like if the drivers had like their phone on videoing their speedometer, right? Then they showed the video to the cops. The cops would have been like, right there, you went 74, let me write you a ticket. That would be if we had that information. That's what this is here. Yeah. Okay. Doesn't it seem reasonable then that if my speed really is continuous, then I'd actually have to hit that average speed? You can see up there, according to my graph, it would be 3 times. It just has to be at least 1 time. This is what's called the mean value theorem for integrals. Right here, I'm not a fan of this blue box. I feel like that blue box is a little confusing the way it's presented. So I'm going to show you this down here. So if f is continuous on the interval from a to b, then there will be some number contained within the interval such that this statement is true. And I want to highlight this for you. What is this right here? That's the average value of x, right? That's what we've been working on for the last 2 questions. So this is the average value of f of x. And then on the right, what's that? Yeah, it's like the value at a point, right? So value at c. So all the mean value theorem for integrals is saying is that if you can calculate the average value, then somewhere on the interval, the function you're finding the average value for has to actually hit that average, as long as the function you're dealing with is continuous. So it would make no sense, right, for This would almost go kind of the speed trap thing a little bit, right? To say, hey, yeah, I realize that you calculated my average speed to be 50, but I never went 50. The only way out of that is to say that you have a car that can follow a non-continuous path, and in the real world, that's ridiculous, we think, right? So far, at least. And so you could say, in other words, somewhere the instantaneous height equals the average height. Saying the same thing. So I thought we'd do one example of this, and I'll kind of set this up for you in pieces, and we'll, again, try to kind of work through the reviewing of how we do definite integrals. From a concept standpoint, does that make sense? A lot of the little proofs and things that I do in here are not like rigorous official proofs. If later on in your math career, like in college, if you ever take a class called Real Analysis, then you'll get into all of these things in depth. It's proof, and at the end of that class, you'll be like, wow, I don't think I used a single number this entire math class, because all you do is you prove things in general. And it can be kind of a challenging kind of frame of mind, right? To think, okay, I'm just going to be dealing with no numbers in this math class. It is challenging for sure. Okay, if you all would, take a look at number 11. Please notice number 11. We want to read the directions all the way through. In number 11, you're kind of given two sets of directions. It says, the first one is really straightforward. It says, find the average value of the function on the interval. So let's just start right there. Let's see if you guys can set this up and execute it. Find the average value of the function on the interval. So this will be the third opportunity to do this. See if you can set this up yourselves and execute it all the way through, and then we'll deal with the other part of the question as well. Like this, 1 over 2 minus negative 1 times the interval from negative 1 to 2 of 4x cubed minus 3x squared dx. Is that what you guys had? Okay, so as you proceed through here, you get 1/3, and then the antiderivatives are going to be x to the 4th minus x cubed. This is evaluated from negative 1 to 2. Again, please practice good notation. It should really look just like that. Then we're going to plug in the 2 and the negative 1. Bless you. We get 2 to the 4th minus 2 cubed minus negative 1 to the 4th minus negative 1 cubed. And that ends up being 1/3 of, let's see, it'll be 16 minus 8 minus 2. And so that would be 6 over 3, which is 2. Okay, so your average value should be 2. Take a look at what you have. Does this make sense? Do you have any questions? Okay, so at this point you've done the thing that's highlighted in red up there. It says, and also find all values of x for which the function equals its average value. So what's the average value? 2. We're supposed to find where the function, f of x, equals its average value. So this would be the equation we would set up to answer that other question, something like this. 4x cubed minus 3x squared equals 2. Essentially what I'm doing here is I'm trying to find the x value where that function actually hits its average. So as far as how you solve that, there's a number of treacherous paths that you could trace through here. What I would suggest and what I would expect in a situation like this is to use calculator. Factoring is not going to help. If you were to do this, plenty of our friends did this. This is getting pretty scary. This is really bad. Right? So this is really, really bad. Remember, it's a zero factor property, not the whatever you want it to be factor property. In this case, a 2. And that number would have to be a 0 for that to work, and it's not. So that doesn't work. I would just use your calculator. And if I remember from the other class, it's like 1 point something. 1.1369. Say again? 1.1369. That sounds about right. You guys agreeing with that? Just the intersection finder or the zero finder, depending on how you arrange it. Did Matt get it right this time? You guys all good? Okay. Take a minute, make sure you know how to do that. If you don't, let me know. Hey, let's say this were a quiz question. Can I talk about points? So I would say on something like this, I would definitely award a full point for you just getting this thing set up, right? Knowing what the average value of a function looks like. With this one, I think the antiderivatives are pretty simple, and so I would give you another point for the correct antiderivatives. And then I would give you a point showing that you did FTC1. That would be another point right there showing that you plugged in and subtracted. And then getting all the way through the arithmetic here to the 2 would be worth another point. And then for the other part, I would say setting up this equation, just like getting that equation set up, that would be worth a point. And then I know you're probably going to use your calculator, so that would be worth just a single point there to get to the answer. So could be a 6-point question. It would be a lot. Just not because there's a lot of details, there are some details, but you have a lot of calculus concepts that you're doing. You're setting up a definite integral, you're finding an antiderivative, you're doing FTC1, you're equating two important things, and then solving to get the answer would be the final point there. Okay, do you have any questions at all? Got one more topic we're going to cover here today, and it is a good one. It's called the Fundamental Theorem of Calculus, Part 2. So Fundamental Theorem of Calculus, Part 1, that's the thing we did last week on Wednesday, or not last week, the week before that, right before we left. We did FTC1. We had the video on that and everything. This is called FTC2. And here is, can I give you the Spark Notes version of this?
Yes.
The derivative and the integral cancel each other out.
No.
That's basically it. That's basically it. The derivative and the integral, for the first time, we're going to come right out and say that the derivative and the integral are inverses, right? They cancel each other out. And that's kind of what you see here. I'm going to, for the moment, I'm going to kind of ignore that stuff at the top, and I'm going to look at the blue box on this one, and I'll attempt to surface level prove it to you. So here we go. If you see something like this, let's notice some important characteristics. Notice the expression on the front. What does ddx mean? Yeah, do the derivative. Like, do the derivative of the thing that comes next, and specifically the derivative with respect to x. But then you look at the thing that comes next, and what's unique about that? It's an integral, and not only is it an integral, it's got some interesting limits. The a, we would say, is a constant. As you guys know, typically letters at the start of the alphabet represent a constant. And then the x is definitely not a constant. This is going to be some expression in terms of x. This is pretty unique. So we're doing the derivative of some integral expression, and the integral has limits from a constant to a variable. Wow, and it's all of f of t. But if you look at what happens here, it says equals, really important symbol, of course. It says equals f of x. So let's like take some stock of what's disappeared. Like, what has just gone away?
T.
The what?
The T.
The t is turned into an x. That's a really important thing to think about. Like, how did that happen? What else has just disappeared? The a is gone, the derivative is gone, and the integral. So like almost everything has disappeared, and somehow the t became an x, right? So you might look at this and say, wow, how did that happen? And we're going to try to answer that question. Two levels to this. I would say the doing of what I'm about to do is kind of complicated. It's not too bad. The good news is I'm going to show you a little trick to kind of navigate that, and it's going to be the thing that I would prefer you do. So I'm going to really, on a very basic level, prove this to you. And so here it goes. Check this out. I'm just going to use this space off to the side, and this will be all the space that I really need for all of this. So here we go. I'm going to write ddx of the integral from a to x of f of t dt. And I'm going to go ahead and do the work on the inside first, right? Just like the order of operations we've done. I'm going to find the antiderivative of lowercase f. Do you guys remember the convention that the antiderivative of lowercase f could be represented by capital F?
Yes.
So that's the convention we'll use here. So I'm going to say my next step would be ddx of capital F of t evaluated from some constant a to x. Remember that a represents a constant, and x represents some variable. So now what I'm going to do is I'm going to use FTC1, and I'm going to plug in the x, and I'm going to plug in the a, and I'm going to subtract, just like we've been practicing. So it's going to be d dx of capital f of x minus capital f of a. And I'm actually about ready to finish this, because if the antiderivative of lowercase f is capital F, what's the derivative of capital F? Lowercase f, right? So this would be lowercase f. And here's the last little trick to this. If a is a constant, what is capital F of a? It's a constant, right? Now think about it. If you've got a function with an input of x, and you plug some number in for x, don't you always get some other constant back out? And so if capital F of a is a constant, I'm supposed to do d dx of that, what do I get? 0, right? Derivative of a constant is 0. I'm simply left with f of x. So this answers all those questions. Like, where did the d dx and the integral go? Well, they essentially cancel each other out, right? That's what made the lowercase go to a capital and the capital go to a lowercase. What happened to the a? Well, the derivative of a constant, just 0. That's why that seemed to have disappeared. The bottom line is we can connect these two right here, and we can use a little trick. But before we use the little trick, I thought I would do one more thing, and I want to see if this makes sense to you guys. What if I wrote this? It's supposed to be a times 1. Why on earth would I write that? Because I felt like it. I do feel like it, but there's another reason. You guys remember the chain rule? Remember, if you are doing the derivative of something and the input is really simple, like an x, you could multiply by the derivative of that input and it really wouldn't make a difference, right? But if the input is complicated, it makes a difference, right? This really is a chain rule thought here, this times 1 thing. So all this stuff over here that I showed you, this is not something you'll probably ever have to repeat. It's just sort of a basic proof of what this is. Can I show you how to actually do these? Like using the FTC2 trick, and you're going to want to do this trick. So take a look at example number 1. You notice a couple things about it. First of all, it's d dx, so it's a derivative. But then you say, all right, derivative, I can do that. But then you look at the thing you're supposed to differentiate, and it's an integral. And not only is it an integral, it's got a lower limit of 2 and an upper limit of x squared. Hopefully what you would do here, quicker rather than slower, you'd be like, oh, I know what this is. This is FTC2. Fundamental Theorem of Calculus Part 2, where the derivative and the integral cancel each other out, right? So you'd say d dx of some integral from 2 to x squared. This has to be FTC2. And here's how you do the FTC2 trick. It's really simple. You take this upper limit, the x squared, and what you do is you drop it in place anytime you see a t. So it would look like this, e to the x squared cubed. Wherever you see a t, you drop that x squared in this case, you drop that in wherever you see a t, and then, according to the chain rule, you've got to multiply by the derivative of what you plugged in. So what do we plug in? And the derivative of that is? 2x. So we'd multiply the whole thing by 2x. So what is x squared cubed really? X to the 6th. Yep. So it'd be e to the x to the 6th times 2x. And this is one where you have to use this FTC2 trick, because not only have we not even talked about e yet, e to anything, even after we've talked about e to the something, this is actually an antiderivative we wouldn't be able to handle. We just would not have the skill level yet to handle this. And so I will typically force your hand and make you use FTC2 instead of doing the thing off to the right. Take a look at that next one. Again, the characteristics I hope you'd notice, really key characteristic, we're doing a derivative of an integral, and the integral is from a constant up to a variable expression. So here's what you do. You take that 2x and you drop it in place of the t. So it's 2x quantity squared, and you have to multiply by the derivative of what you plugged in. So on this one, you'd multiply by 2. So this in the end would be sine of 4x squared times 2. We got like 2 minutes here. Can I just do one more really quick, just to see how you guys are doing with this? So try this one. So really the key is to recognize FTC2, use the trick. So let's try this one. DDX integral from 12 to x cubed of natural log of t dt. Anyone want to offer an answer on this one? Go ahead, Matt.
Natural log of x cubed times 3x squared.
Or natural log of x cubed times
3x squared.
3x squared. He's got it, doesn't he? Yep, right on the money. That's really, really good. Okay, so that's FTC2. If you can keep track of that trick, it makes life really, really easy for